the Hebrew University over there. And Yael will tell us about EMRIs in Kerr Spacetime. Just to explain, EMRIs are
an extreme mass resonance spiral is where you have a compact object, like a stellar black hole or a neutron star, that is slowly in-spiraled around a massive black hole.
right.
So it's going to inspire many, many cycles, so we hope to see them in these cycles.
Yeah, so these are combinations, binaries of two black holes with very different masses. For example, if you have a satellite galaxy going to the center of the galaxy or a globular cluster bringing the black hole inside. And so we'll hear about EMRIs in Kerr spacetime, the role of inclination diffusion. And after that, we'll hear from Henry Whitehead from the University of Oxford, where English is spoken much better than here. And he will tell us about gas-assisted binary black hole formation in AGN. So that relates to EMRIs as well. And then finally, we'll hear from our own Daichi Tsuna, who will educate us about white dwarf mergers and the history of supernova 1181. And when was that one?
In 1181.
So that was a while ago. Yeah. We'll hear more about it. Let's hope that the display works. It's not working?
We might be approaching
Okay.
using the whiteboard.
Okay, well, let's do that then. Going back to old fashioned astrophysics, let's forget about AI systems. Let's forget about electronic displays.
We sure are. I'm going to go get an eraser. Two colors.
Boy, I will you know what? I am gonna like look at my thing so I
Okay, Robyn, go ahead. This is actually also a test of the teaching capabilities of the presenters today.
No, I feel like I'm
summarize all the information in a small number of lines on the board.
all right. Hi, everyone. All right, this is going to be impromptu. I lied to you. I'm going to talk about something else because I ended up talking about the globular cluster stuff in my colloquium. So I didn't want to bore all the people that were so kind as to come. So what I'm going to talk about instead is a paper that one of my grad students and I recently put on the archive about how you can constrain the UV background at reionization with tidal streams around the Milky Way. Okay, so this paper is there. Okay, so what this is based on is this thing that people call a near-far method for reionization studies. So the way this works is that you go and you observe a bunch of nearby low-mass galaxies, and then you make, I'm going to embarrass myself now because I'm not an observer. You make the CMD, and then you model it to get a star formation history. Right? Except for these little galaxies, this thing basically looks like this. Right? So this is now. All right? So then you say, okay, well, I want to go back in time everything before that point existed at reionization. And then you turn that into a number for the UV luminosity, and you add it to the UV luminosity function at high reg. All right. So the problem is that like most of the little stuff that is in the local group is not a galaxy anymore. So when you do this, you're missing everything that was ever tidally destroyed by the Milky Way, and that turns out to be like half of the contributions from low mass galaxies. So just for that reason, we wanted to know whether it would help this process if you could add those things in, because constructing the CMDs of tidal streams around the Milky Way is already something that people do. They've also started to do it already for things that we call phase mixed objects. So they've been in the Milky Way's potential so long that they don't look like a stream anymore, so their stars are all over the place. But you can sometimes still find these if you have their full kinematic information. So what happens if you add those things to the this process, right? So the end result of this is something like this, right? So up here at the big end, you get this part from direct observations with JWST, and then down here at this end, you're supposed to get them from this thing. All right, I'll come back to it, but the difficulty with this is that the overlap, which as I'm showing here, is not very big between the stuff you can see with JWST and the stuff you can reconstruct locally. So that's one of the challenges in doing this. Anyway, so what you can do is you can look at how much of this function you can reconstruct based on the state of the stuff, right? So the first possibility, this is actually, I'm gonna do what it says in the paper. So we go up to about -16, and this is at Z of 7, I think, yeah. So we tried this out with cosmological simulations of Milky Way mass galaxies. They have a few limitations when it comes to reionization. So one is just that everything is really low mass back then, and so you run up into resolution limits very quickly. And the other is that the UV background is like uniformly imposed. So these are not simulations where individual like stars are reionizing their local background. You just get a UV background and you apply it to the simulation. So those are some generalizations that I'm still a little curious how they affect what our conclusions were, but people had tested this out with just the satellites and field galaxies around the Milky Way analogs and found that it worked pretty well. But when you do that, so if you were able to perfectly dissect everything that came into the Milky Way ever, you would get this. Okay, if you just use things that are intact, you sort of get this. Right, this is like log n. Or maybe log phi. Yeah, it's the density. So this is if you get okay. And the difference between these two slopes is it varies quite a bit when you go from halo to halo. And another worry that people have about this technique is we only have one Milky Way or local group or whatever to do this in. So we have to kind of get lucky that it's something that's somewhat representative of the general population of galaxies to extend this understanding to the rest of the universe. But I wonder if this one works. Yay. All right, so you can do better if you add the tidal streams. So these are things that we can still tell used to be a galaxy. And you do even better if you add all the phase mix stuff. So these are cumulative, so they also include the galaxies. And so in the end, you get up to being able to reconstruct a little better than 50% if you could put everything that you knew about from each of these populations back into your sample. But I've elided over something here, which is that when you do this, you assume that you ignore the assembly history of the individual galaxies that you're doing, so you just say that each one of them is whatever stellar mass it is, right? And if you do that, this gets a little bit worse in every sample. Regardless, so there's like two advantages to doing this with throwing in whatever other stuff you can find and analyze besides just the galaxies. One thing is that the halo-to-halo scatter gets smaller. So the more complete your accounting of all the ingredients that went in, of low mass things that went into the Milky Way are, the better you can, the less susceptible you are to the differences in the accretion history of your galaxy versus another. So there's less halo-to-halo scatter. The other one is that you get better overlap with what you can see with Webb. So a lot of the things that are now all mixed up in our galaxy, either as tidal streams or phase mixed stuff, as a population, they are more massive than the ones that are today in intact galaxies, either as satellites or the field at low masses. And so what that does is it extends this out here a little more so that you get, so that, here you're really measuring something that is, at least we hope, representative of the grand distribution of galaxies. We're never going to get the normalization of this right, but we can hope to get the slope right. But you need to match it onto J2ST in order to get the normalization back to where it should be. So having a little more overlap here is a good thing, because you can at least do some consistency checks in the region where you can see the thing at high redshift and then see what you reconstructed it to be at low redshift. So that was our first test, and now we're going to go and look at see how much of this you could actually detect and add to the sample, which is another can of worms. So stay tuned. That's it.
That was perfect. 8 seconds. My question is, JWST detects very bright galaxies, and one of the interpretations of why they see much more light than we expected is population 3 stars, very massive stars. Those are dead by now because they have a lifespan of a few million years. So obviously you won't find them in the Milky Way galaxy, and you won't be able to know that there was an early phase of very bright emission that is part of the Webb data, but it's not found anymore. So what do you do about that?
Oh, I don't know. It's funny, I was actually asking Kaylee about this this morning, because she's been experimenting with these models where you have different kinds of POP3 stars in there, and what happens to these little guys. And it depends on what the cutoff at the high mass of your POP3 IMF is what she told me. So if you have too many massive stars, you blow up a bunch of galaxies before you get to the present day. And then that's one kind of bias. And then if you don't, then maybe they shift, like you said, the brightness of these. So matching the normalizations here is the wrong thing to do. Our simulations don't have POP3 stars in them, so they're they represent the assumption that that's not going to be a big deal. But I agree that that's something for all you reionization people to work out. I co-advise Zaritra, who is the first author on this paper, with Adam Lids, who's also at Penn. So I've learned a lot about reionization from this work.
Any other comments, questions, anyone?
Oh,
Yes.
so what does this actually allow you to learn about reionization?
It tells you what the UV like luminosity density was back then. So how many ionizing photons are around to do reionization.
As a function of Z?
As a function of redshift, yeah. So in the paper we did this at multiple redshifts, but I wasn't going to draw all of them on the board.
Yeah, we're missing
It's
some.
very important because what you're doing is very important because the low luminosity end might dominate the production, and so you want to complement the web data with the low luminosity.
Absolutely. And what you conclude about how worried you need to be about the low luminosity end changes when you add in the other stuff. It actually changes the proportion of the ionizing background that comes from the low mass stuff. I think you end up saying that it's more weighted towards the low end once you add in the other things, because they also tend to be things that formed a little earlier because they've had time to like be a galaxy and then be like destroyed by the Milky Way. That's a very like top level thing, and in fact there's a lot of scatter in this just from the process of hierarchical accretion being so widely variable within environments. The other thing that affects this is whether you look at the simulations that we have that just have a Milky Way-like system or the ones that have the Milky Way and an Andromeda in them. And so those form a little earlier, and you get better agreement for those than you do with the like global UV luminosity function than you do for the later forming isolated systems. And just the difference between the Milky Way being in a void and being in a local group is enough to help with that, which I think is good.
Let's thank Robyn again.
Thank
Hi everyone, my name is Yael, and I will talk about a recent project with my advisor Nick Stone and a collaboration with Scott Hughes. So as I described, EMRIs is where you have a supermassive black hole and you have a small compact object, like a stellar black hole that is orbiting around the massive black hole. If it orbits around it many cycles, then you will get an EMRI, and then we will see it in LISA in the future. The issue with LISA is that it's going to see everything at the same time. So in order to see something, we really need to know what is the EMRI rate. And currently, the estimate for the EMRI rate is highly uncertain and is spanned over 3 orders of magnitude. So we need to study them a bit better. So the big question is how you can make a compact object get close enough to the massive black hole in the first place. Today I will talk about one formation channel, which is the lost cone, which is when you have a compact object or a star in a cluster, then two-body scatterings between the different objects will cause to small changes, small stochastic changes of the energy and angular momentum. And then at some point, if the velocity of the object, let's say that this is the massive black hole, and you have the stellar black hole, which is orbiting around it, then if the velocity of the object will enter into a conical region shape, like that, then it will get closer to the black hole and can get captured, totally disrupted, or slowly inspired, and then you get an EMRI. A better plot to understand what's going on here is if we plot the semi-major axis is the function of the inverse of the eccentricity. So far away from the black hole, two-body scatterings are going to be dominant, and then we will have small changes in energy and angular momentum. Once it gets close enough, and we get to a region, and we'll pass a radius. This is the equal, we'll talk about it in a second. Then if the pericenter will pass the equal, then it will plunge directly into the black hole. This is the less parabolic orbit. It means that the only orbit that can, once the percenter is here, the only orbit that the object can move is directly into it. So no gravitational waves, no detectable by LISA. But if first it reached to another region, reach to this region, where gravitational waves are the dominant component, more than the two-body scatterings, then you will get an error. So these two lines define a critical semi-major axis. So if the initial semi-major axis is below this semi-major, if this initial semi-major axis is below this critical value, then you will probably get an error because you get into that region. But if you start with above, with a larger critical above semi-major axis, then you will get to that region, no EMRI, just a plunge, no gravitational waves. Here there is supposed to be a movie, just to show you how it's going to look. So you have far away from the black hole, two-body scattering is dominant. So you have some small stochastic changes. If it gets closer, then you will enter to that region, gravitational wave will get into it, and then you will get an error. LISA is going to detect things here. If you are far away from the black hole, but with a large major axis, then you're scattering around, get here, no EMRI, no gravitational waves. Cool. You can see this separation also in a function called the S function, as a function of the same major axis, where the S function is the number of EMRIs over the entire number of captures. So it's the number of EMRIs plus the number of plunges. Okay. So if we plot that picture here, then for small semi-major axis we'll have 100% EMRIs, and for large semi-major axis we'll have 100% plunges. And in the middle you will get something like that. Cool. But this has been done with assuming that the massive black hole is non-spinning. But we know that massive black holes in the universe, many of them at least, spin rapidly. So things are going to change. So how it will affect the EMRIs? This radius, the less parabolic orbit, the IPCO, depends on both the spin and the inclination. So if we plot the IPCO as the function of inclination, for non-spinning black hole it's just a constant. This is non-spinning. But if the black hole is spinning, then it looks like that. Let's say 0.9. So it means that for, this is a prograde orbit, so let's say 0, this is retrograde orbit. So for prograde orbits, the IPCO is smaller, so it means you will have more EMRIs. But for retrograde orbits, it's larger, so we have more plunges. So this picture is a bit different. You don't have just one IPCO that defines one critical semi-major axis, you will have a range of IPCOs that define a range of critical semi-major axes. So it will affect the EMRI rates. This has already been investigated before, and they found that for highly spinning black holes with small inclination, then the EMRI rate will increase by a factor of 13. The problem is that the inclination is assumed to be fixed. But we know that two-body scatterings are going to change also the inclination. Not just the energy and the angular momentum, but the energy, the angular momentum, and the inclination. So in our project, we decided to move, instead of just investigating the change of the energy and angular momentum, to investigate the energy, the angular momentum in the z direction, and the Carter constant. If it's the first time you hear about the Carter constant, you can think about it in the far-field limit as the angular momentum in the x and y direction squared. And another thing that we investigated is what happens if you move from a Keplerian orbit to a geodesic. So we developed the mathematical framework to move from 2D to 3D, and the result is similar to that, but you need to imagine the colors. So the colors are going to be the inclination. So if I start the inclination is one color, then it will be very different after a few orbits. Let's do it. Imagine that you have a movie of the inclination over the pericenter. So if you start with specific inclination, it will not stay there. It just move around. It just move around. So even prograde orbits that were progrades become retrograde and vice versa. So after that, we came back to the S-curves, and then we, if this one is the 2D case with a non-spinning black hole, then if you plot again 2D case with again non-spinning black hole, but now this one will be with geodesics, then you will have more EMRIs. Only that you will add more EMRIs to your sample. But if now we add also the spin and the inclination diffusion, then we get even more EMRIs. It will move even further out. This is, let's say, 0.9. So the take-home message is that the inclination is not fixed. You cannot assume that it's just constant. And it's also it's more important when you add spin to the system of the massive black hole. I will just note that I talked about EMRIs, but also TDEs are like one of the formation channel for TDEs is also the loss count. So it will be relevant also for TDEs and also for QPs if you are interested. So thank you for listening.
That's excellent. We have 1 minute left. I should also comment that when teaching classes, the students very often say that using the board is a far better method because then the audience can follow. So you benefit actually more attention as a result. One question, when you have spin to the black hole, there is frame dragging, the lens steering effect. Does that in any way come into play or not?
Yeah, so this is entering into the moving from Kepler to geodesics.
Okay, that's the lens steering.
Yeah.
Okay. Ramesh?
So this is good news for Lisa, right? More EMRIs. Yeah, but I was wondering quantitatively, are you talking about tens, factor of tens, or factor of a few? How many more?
So in the extreme case, where you hear like really prograde orbits high spin, then the most EMRIs that you can get is a factor of 30. But this is the extreme case. This will not be there. So you will have more EMRIs, but not that.
But if I average over random orientation?
Yeah, it's still a work in progress, so I don't have a number.
You don't have a number?
Yes,
okay.
yes. You need to integrate the scale. Yes.
Any other questions? Morgan?
Oh, go ahead.
No, it's okay. Morgan first.
So I'm curious if some of these orbits are also precessing because of the stellar mass distribution, which is sort of another small effect. Does that affect things in a similar way to the precession that's imparted by the relativistic?
So there are several effects from the stellar cluster.
Yeah.
We include only the two-body scattering.
Yeah.
So you have more, we didn't include them. For example, you have the scalar resonant relaxation. Previous research showed that scalar resonant relaxation will not change things, but maybe vector resonant relaxation will, because we are talking about inclination, so
Yeah.
this is the next step. So
Interesting.
this is a future project.
Okay, thanks.
Last question, Tony.
So just to get an idea here, so if you have a billion solar mass black hole, about how big is A sub C hand waving? It's a parsec or?
No. The radius of influence is parsec, so it's like it's less. It's like 1,000 RG, something
Okay.
like that.
So that's like a tenth of a parsec or a few percent of a parsec.
Yeah.
Okay.
Yeah.
Okay, thank you so much. Yael.
Thank you.
Okay, right, thanks for having me here today. I'm going to talk a little bit about some of the work I've been doing on hydrodynamic simulations of stellar mass black holes embedded within the disk of active galactic nuclei. It's been a little bit hard to draw what's going on, because normally I've got about 10 million cells all evolving in time, so I'm not going to try and do that. I'll try and give it a schematic description. But the reason why I'm interested in looking at these kind of objects is because I'm interested in motivating where we might find the merging black hole binaries that we detect using the LIGO, Virgo, and CAGRA ground-based gravitational wave observatories. So we know that black hole binaries are merging somewhere out in the universe, but it's not exactly obvious where these binaries might be found. Are they existing in the field, within globular clusters, or within some more exotic environments such as an active galactic nucleus? And the reason why AGN has sort of come to the forefront of imagining where these binaries might be coming from is because they've got a lot of advantageous properties for forming binaries that will merge within a Hubble time. All right, so we need to form black hole binaries that will harden sufficiently quickly to merge at the rate that we can detect them currently. And AGN have a lot of properties that are favourable for that. They exist within nuclear star clusters, so we've got a high number density of compact objects to begin with. And they've got a gaseous disk, and this disk acts as a dissipative medium that can remove inclination from the nuclear star cluster, aligning black holes with the disk. And this dissipative medium can help form binaries during close encounters and harden the binaries down to merger faster than gravitational waves can allow. So you can merge these binaries with gravitational wave, but only when they are already quite hard, otherwise it takes simply too long. To investigate this system, I've been performing simulations in something called the shearing frame. So we've got a supermassive black hole in the middle of the system here. We've got a huge AGN disk around it, and it's simply too expensive to simulate this entire disk simultaneously. So what we do is we take a small section of the disk, called a shearing box, which rotates around the supermassive black hole at the same frequency as the background gas, and we do all of our experimentation in here. So within this box, I'm going to investigate dynamics between two stellar mass black holes, each on circular orbits about the supermassive black hole. But in this box, those orbits look like straight lines. So one of them is going like this, and one of them is going like that. Okay? And now in this gas-filled box, they're going to have some complex interaction with the gas, with each other, and we're going to see how this initially unbound system may form a binary. All right? That's the question we're really trying to answer here, is how efficiently can we form binaries in this AGN embedded system. And in order to do simulations in here, we need to be careful, because we need to consider not only the gravity of the supermassive black hole, but also the fact that we're in a non-inertial frame. All right? So the fact that we're in a non-inertial frame introduces a few extra forces that we need to consider. So within this frame, I'm going to define a Cartesian basis located at the center, and we get additional forces because of this. So I'll just call this A SMBH for brevity here, and there's three forces that we need to consider. The first scales with this x parameter here. This is our radial displacement. This is sort of like a tidal force. So this is the balance of the centrifugal or centripetal acceleration with the radial supermassive black hole gravity. We've also got a term that looks like the cross product of the velocity of whatever object you've got and this rotation about the central object. This is your Coriolis force. And finally, there's a term due to the vertical gravity that looks a little bit like this. And they're all very important when it comes to simulating dynamics in this frame. The presence of the supermassive black hole does make a difference. This isn't just a wind tunnel that we're in, or a lone system. It does affect the gas dynamics. And if we run actual simulations like this, we can see what happens within the box. So initially, I'll draw a box with just a single stellar mass black hole in it, and we see that the gas forms these spiral density wakes. So this is well understood in the protoplanetary sort of community. This is just establishing in an AGN context. But if we look at this system edge on, so now this is my vertical direction Z here, we've got some bar of gas, which is the disk initially. We might track this for up to, say, 10 scale heights. When I put a black hole into the middle of it, what I see is that the black hole gravitates gas towards it in the midplane and then blows out an outflow above and below the disk. Okay? So this happens because we're building up a hot accumulation of shock-heated gas around the black hole. As gas is rammed into the system by the ambient shear, we generate a wind. All right? So this isn't simulated on relativistic scales. We're still at the sort of, AU plus, tens of AU outwards. And we can generate this wind purely from thermodynamic effects. And this wind has some interesting properties that really only occur because we're in a rotating frame. If we look in the midplane, and we look at how the gas is rotating about the black hole, we find that it has a consistent prograde rotation. Okay, so this is expected from the action of the protoplanetary community already. But if we look in the wind, so now we look above and below the midplane, what we find is that actually the flow is rotating in the opposite direction. All right, And this might seem a little bit strange. There's an inflow and an outflow that are rotating in opposite directions. But it's actually just a direct consequence of this Coriolis force. So what we're looking at here is an astrophysical example of cyclogenesis. Okay? So things that are moving inwards, so this is accretion in the midplane, spin one way because of this cross product term that we've got here, and things that are flowing outwards in the wind rotate in the opposite direction. Okay? So what we have in the midplane is a cyclone, and above and below it we have an anticyclone. So what this system looks like is a sandwiching of cyclone between anticyclones. And while these simulations that I'm running currently don't have magnetic fields, there's some interesting consequences you can think of about what would happen if magnetism were to be included in this system. So if we thread this environment with some vertical magnetic field structure, what we're going to end up inducing is a strong twist in the field, because we've got these two flow structures that are counter-rotating with respect to each other. This is something we really want to follow up with MHD simulations, because it's a potential for all kinds of high-energy effects, such as reconnection or stronger wind outflows based on this twisting of magnetic field structure. The thing I wanted to touch on briefly here is the actual premise for this full simulation, which was looking at binary formation. So what happens now if we have two black holes initially on these circular orbits that have some complicated interaction with each other? And we can simulate what happens when these two wind systems collide. And what we find is that as the two systems get very close to each other, these shock-heated bubbles of gas crash into each other and generate even stronger outflows. So what you see here is, if I look at now, this is looking at one stellar mass black hole in the center of the frame and another black hole coming into an encounter around it. It comes in, and it will do something that looks like this. So we form an eccentric binary during this close encounter because the gas around each black hole slams into each other, can't keep up, and so exerts a drag. And this drag removes orbital energy from the system. So the black hole comes in here, and each pericenter passage it goes through, it loses orbital energy, it shock heats the gas further, and it generates a strong quasi-spherical outflow. So in the lovely simulations that I can't show here, you'll see repeated collisions which kick out these huge amounts of gas. So you're able to steadily harden this binary over time. We ran a lot of different simulations for this, 145 of them, looking at 15 different initial trajectories and 9 different AGN environments, looking at different gas densities, distance from the supermassive black hole, gas temperatures. And we found that the overall determinant for whether or not a binary would form during the interactions is a quantity called the Hill mass. So this is the amount of gas that's inside of the ambient Hill sphere of the system. And this Hill sphere is a measure of the sphere of influence of an embedded object, and it scales as the distance from the central object and this factor, which is a ratio of the minor, being like the black hole and supermassive black hole masses, something like this. So it's effectively how much gas you have within your ambient sphere of influence. And because it depends on the distance from the supermassive black hole, the main takeaway is that it's much easier to form binaries further away from the supermassive black hole than it is very close to them. There's quite a strong correlation between the two. If you plot the amount of mass in the Hill sphere compared to the black hole mass here, you find that the trend looks something like this for the number of successful binary formations. So gas poor, very few binaries. Gas rich, effectively all systems form binaries. There's lots of complicated n-body dynamics that go into these close encounters that's not covered by this mass description, but statistically you can get a reasonably good description just by looking at your ambient system and seeing how much gas is available. Got no clue how I'm doing for time.
Amazing. 1 minute.
1 minute. Okay, awesome. I'll leave it there then.
So first I wanted to compliment all 3 presenters. That was amazing. And you are on your path to become excellent teachers. And I guess in the context of what you described, you can double the number of publications you have by applying everything you did also to protoplanetary disks, because it's exactly the same situation.
I think the unfortunate truth is the protoplanetary disk community have done it already.
Exactly. So that was my question actually. Is there anything that you found that they didn't find?
Yeah, so actually when you look at these flows in the post-planetary disk community, you get something that looks very different. Actually you find the accretion onto the compact object, or the objects in general, generally falls in down through the poles rather than driven in the midplane, and this is just because the angular momentum barrier doesn't exist for stuff coming in down the poles. The only reason you get this different flow structure in the AGN embedded case is because the gas is so much hotter the pressure gradients become so much more important. So actually, you almost get the opposite scenario in terms of like embedded object morphology. Previously, people were running these AGN simulations isothermally, so not including the heating of the gas from shocks, and they got something that looked very similar to the planetary case. But when you include the shock heating, you see that it looks very different. So that's the distinction between the two of them currently.
Interesting. By the way, do we have binary planets?
I'm not sure.
I don't know. Does anyone know if we're
No binary planets.
Are there?
Can you
No.
count the Earth and Moon?
No binary planets.
No binary planets.
Yeah, so
Except for Pluto.
why do we have binary black holes and no binary planets?
It's a great question. Maybe they are.
You might write a paper about that. Yeah, because if you get binaries, why doesn't it happen in planetary disk?
I'm not sure. Maybe it depends on the lifetime of the disk systems.
It would be
and
nice
the
to
ratios
answer
and so
that.
on.
We haven't detected the moon for sure yet also.
Yeah, we're working on it.
Okay. Morgan.
What does the role of the relative velocity play? So as you go out in the disk,
Yeah.
you move more slowly,
Mhm.
presumably relative to each other. There's less
Yeah.
like shear between, and then that enhances the gas drag.
Yeah, so it's a little bit tricky because people do tend to think of gas dynamical friction of like moving slower is good in terms of removing energy, but this system behaves a little bit differently to like standard like Ostraker gas dynamical friction in that we don't really see that strong correlation between velocity and dissipation, purely because it's really during these close encounters where you're actually moving very quickly that you remove a lot of the energy. In terms of the actual relative velocities in the ambient system, we tend to parameterize the distance between the two of these in terms of the Hill radius, so some multiple of this, which means it's a bit of a wash exactly how far you move in and out because there ends up being a scaling. The velocities in this system have, the ambient velocities look like Q omega x distance from the center. So if you're parameterized in this, the ambient velocities don't look very different for the setups that we're looking here.
So you're saying the gas is so centrally concentrated around the black hole that most of your dissipation happens there?
Exactly. Yeah.
Okay, but that's a function of the density profile times the velocity.
The density profile of the ambient system.
Like you have a density profile that's concentrated towards the other object
Yes.
in that
Mhm.
space. So that's interesting.
Yeah.
Okay, let's thank Henry.
Abby, Pluto is a binary planet. Well, it's not really
Sorry,
a planet.
there are?
Pluto and Carol in our solar system, you can consider it as a binary planet because the mass ratio is very close
Is
to
Pluto a
it.
planet?
It's a matter of terminology. And it's far, far away. Maybe
Oh,
it'll
no,
give you
for
some
sure.
idea.
We're about to do binaries, but they're not planets.
So this is what my talk is about. So I'm Tsuna, I'm a new ITC fellow here. I'm going to talk about this historical supernova called supernova 1181. It was found in the northern sky near Cassiopeia, and it was found in 1181. And there has been various arguments on what the associated remnant is. And this kind of got solidified only very recently, like a couple of years ago, to an object called PA30. So there's an amateur astronomer called Dana Taptic who was looking at WISE archives to search for like blobby stuff. And this is his 30th object. So that's why it's called PA30. And it's basically a spherical blob. And it's actually in parsec scales. And spectral observation of this found that this is actually expanding with velocities 1,000 kilometers per second. So if you divide the parsec with this, you get roughly 1,000 years. So the time scale was right, and the sky location is consistent with what historical records indicate. Okay, so what was interesting about this is that, so once this association kind of got secure, people started looking into this in more detail. So one of the discovery was that there's this bright central star inside. And you take the spectrum, and I'm gonna not draw very detailed spectrum. But the spectrum is basically from the central star, but it's very hydrogen helium 4. So we have carbon, oxygen, neon in the spectrum. And particularly, there's a very thick oxygen line, oxygen 6 line, very highly ionized. And this thickness corresponds to a velocity of 15,000 kilometers per second, very fast. Okay. So what can make these kind of spectrum? And people have speculated that this object is a very compact white dwarf that is emitting a very fast wind. So, and what kind of white dwarfs can do that? So people have come up with this theory to explain it by white dwarf mergers. So white dwarf mergers, they might have very highly magnetized white dwarfs in the remnant. They might be highly spinning. The abundances look sort of right. And what's more importantly, you can make these theoretical models of white dwarf merger remnants predict that they leave behind this very hot white dwarf, because you need an oxygen 6 line, a hot white dwarf in the HR diagram. So when I draw an HR diagram, so initially, when two white dwarfs merge, the less massive one becomes disrupted. And then you have a more massive white dwarf core with a less massive white dwarf remnant envelope. And the heat generated by the merger necessitates the envelope to puff up. So initially you can start here, but the envelope puffs up to near the Hayashi limit, where stars basically are convective there. You have a very convective envelope. And the star keeps on radiating the heat emitted by this, generated by this merger, until when a significant fraction of the heat is emitted, it contracts by Kelvin-Helmholtz contraction. Okay. So what people think is, what theoretical models indicate, and these indicate, is that we're seeing something here. Okay. So there are two issues to this picture. One is that the time scale for this to evolve is actually quite long. So this takes 10 kiloyears. If you look into these theoretical models. So if you think the merger happened in 1181, and that is a plausible assumption, then you need to make this in 840 years rather than 10 kiloyears. That's one problem. And hope that was time. Second puzzle is Chandra observed this in X-rays and found this very central source. Okay. So it is resolved to be percent of a parsec. And you can have these like X-ray source in a compact object. And one natural thing you can imagine is that, okay, this wind is hitting the ejecta. It's like a pulsar wind nebula. You have some shock that is emitting X-rays. The issue here is that you need the mass of the merger, the ejecta, is not that large, and most of the mass is at parsec scales. So there's only a tiny amount of mass here, so the wind doesn't decelerate that much. If you do detailed calculations, the wind reaches, the shock reaches this radius in 20-ish years, 20 years. So the conclusion is that the wind has to start 10 years before now, although it had 840 years. And this is a really fine-tuned number. So these two issues are in this supernova. And the theoretical model I'm going to talk right now in years' time is a possibility to resolve both of these two. And it's related to the phase where the stars popped up. Okay, so this is sort of analogous to like an AGB star, where you have you have a star that's inflated to near the Hayashi track, and it keeps shedding mass until it reaches the white dwarf. And previous models didn't really take into account this possible extreme mass happening. So to actually physically try to do this, very recently, Jim Fuller and Caltech and myself built a model to try to estimate the mass loss of these stars at these like very puffed up states. The paper is called Boil Off of Red Supergiants. If you want to take a look, you can search about it. But it's not like a prescription, but we built a physical model that sort of reproduces the mass loss rates of red supergiants. Okay, so what happens if we apply this to here? The object is radiating close to Edison, and it's very expanding. So what we find is that at this phase, if we use this model, we predict a very extreme mass loss, about 10 to the minus 3 volt masses per year. Okay, so this actually sheds most of the envelope that's formed by the less mass star in a timescale of centuries. So you're basically not evolving up here, but you're basically shedding all the envelope like halfway or somewhere in the middle, and you're basically bringing the star to the blue phase. So this accelerates the transition to the hot state that's observed today, by maybe a factor of 10 or a few tens depending on the model. This also solves the other problem of the very fine-tuned nature of the onset of the wind, because you're not going to just have the ejecta, but you have this very dense mass outside made of the mass loss at this phase that the white dwarf wind has to travel. So you're going to have a very thick wall, basically, that the wind has to sweep up. And the wall is basically much more massive than if it was just a supernova 1181 ejecta. So detailed calculation of the shock propagation we did in this work indicated that the 10 to 20 years is sort of alleviated by a factor of 10 to 100, 200 years. Okay. So the final picture that we have in this model is correct, and very skeptical at this stage, but the final picture that we have is that 1181, this supernova happened, merger product was formed, and it kept shedding mass loss, shedding mass, and became a hot white dwarf a few centuries later. And then the white dwarf basically made a ring that formed the X-ray that we see now. Okay, so that's the picture. And sorry, I'm a bit.
So Daichi, this is a time scale you're talking about. This is something that you can hope to make predictions and test them in the coming decades and during your career. So what's your...
Yeah, I was about to talk about that if I had the time. So thank you for the question. So one of the tests we can do, and we have a Chandra proposal that's accepted, is that we can actually try to probe the shock. So it's resolved by Chandra. It's barely resolved. But if the scenario of the wind being launched 10 years before, 10 years ago is correct, then within like a few-year baseline, we would definitely see the shock evolving this rate, evolving this time. So we can make a direct test of this kind of scenario. And the other scenario I've thought about is that during this phase, it's basically very dust and shrouded. So it might be possible to search for these like very far infrared sources, far infrared bright sources, maybe in the Milky Way and nearby galaxies. That might be a direct test of this mass loss picture.
Thank you. Any question? Go ahead, Daichi.
Thanks for the great talk. I'm with you that maybe it's very difficult to face a white dwarf just because the way the gas is being emitted. So AGB part solves that, but you also say there's no nitrogen there and there's strong oxygen lines. Also, the mass loss rates are close to what I would say like a Wolf rate star. So is that like something you?
Yeah. So I think
a Wolf rate star.
I think if it's like a CO white dwarf merger, it's kind of hard to make a lot of nitrogen because there's no CNO cycle happening anymore. So, and then yeah, I think. But what was the question about Wolf?
But if you take AGB stars, they should produce a lot of nitrogen. That's like
that's correct. Yeah.
So if we don't see nitrogen there, then maybe it could be a Wolf rate star, given we can match the mass loss rate and.
Oh, this is a carbon, like carbon nitrogen. No, actually, this is a white dwarf that's AGB-like. Like it has a heavy element envelope.
Yeah.
That's
so
heated up.
There's no hydrogen burning or CNO cycle happening anymore here.
Okay.
Yeah.
Okay.
Okay, let's thank all the speakers today.